All right, good morning, everybody. Welcome to our webinar today. We're going to be talking about using SOLIDWORKS to design some battle-tested 3D printed parts. I am Robbie Hoyler. I'm one of the technical solutions consultants here at TPM. I lead the team as the manager, and I am a SOLIDWORKS Elite Application Engineer. Today, we're going to take a look at a couple of case studies. And first of all, I just want to introduce you guys to some of the concepts that we're going to look at. In this webinar, we're going to demonstrate the power and flexibility offered by the SOLIDWORKS product family to rapidly design, create, and test usable replacement parts. And we're going to do that using the Markforged printer. And the data set is going to be our 150-pound robots that are built in the back room at TPM Charlotte by a bunch of high school students. We're going to show you guys how simulation can improve the performance of these parts and push the limits during competition. And we're going to teach you guys how you can ditch some of the low-grade plastic parts that you guys see in manufacturing and replace them with superior quality. So first, I want to introduce the data set. This is our 2019 robot from the first robotics competition this last year. And throughout the competition, we had a couple of interesting challenges come up, and the number one challenge was we had to pick up this plastic polycarbonate disc that you guys see here on the screen, and we ended up 3D printing a series of assemblies to prototype and test that. The final result looks like this robot here. You guys can see the robot picking up and placing, scoring some of the game components here. The robot went up to about 9 feet tall. It had to pick up several parts and whatnot, and part of the challenge for this competition is that the robot had to resist quite a bit of dynamic impacts like you see there, falling over, other robots bumping into us, pushing us, slamming into stuff at top speed. So the parts had to be very robust, and it's a little bit different than what you would see in manufacturing, but a lot of the same design constraints are still in place for something like this. So with that being said, let's take a look at how we got to this final end product. So the parts ended up at the final. We ended up 3D printing a series of different parts for the assembly. So let's take a look at how we did that using SOLIDWORKS. So the challenge was really interesting in that this part had to do a lot for us. So it had to grab the disc off of the wall and it had to place it. So we used SOLIDWORKS to determine what the geometry was going to be and how to design it from a machine design standpoint. Typically we use metal for those parts, but in this case, because the shape was really strange, we saw a design based on the Jaws of Life, which was actually another SOLIDWORKS demonstration that we saw. We tried to design our own Jaws of Life to go inside of the center of this disc, reach out and pull it off of the wall, and then we had a mechanism behind it to push it off and score it and hold it on with Velcro. But the geometry was pretty specific because of the type of drivetrain we used. We had to get aligned really quickly. Another challenge was that the metal copies of this, if we were going to design this out of aluminum, we would have to machine that. And for high school students, that's a pretty intricate and tough thing to machine quickly. It's expensive to machine because students are going to make mistakes. And then our weight is always a concern. We only have 120 pounds to play with for the entire assembly, so every couple of pounds really counts. And we really wanted to see if 3D printing could really replace that. So what you see on the screen was actually our first prototype set of jaws that we actually had slapped onto a test chassis. I'll actually show you guys what that little test chassis looked like. It's basically just a little 8-wheel drivetrain and then slapped on top with a bunch of metal, plywood, and 3D printed parts. You could see us playing around with that one. And the thing that we kind of learned by doing this test this way is that these parts they will fall apart pretty quickly. So we kind of knew from our expectations that plastic parts don't always make the best material, especially when you're ramming into stuff and people are running into you, etc. So manufacturers are going to have a lot of the same concerns in that, are these parts really going to last with a lot of heavy usage? So what we decided to do was to really see if we could actually use SOLIDWORKS to design some parts that would hold up to our uses, and see if we could trust these parts a little bit better than we could in the past. So the first thing we did was we designed our first run-through set, and we ended up with this little triangle shape. And then through a couple of iterations, we found that with interferences on the field and with how the students were driving the robot, there needed to be different shapes that we ended up going with. So we actually ended up printing the first set of claws out of onyx, which is a Markforged material. We'll talk about it a little bit later. And these claws did us pretty well. We installed one set of these pieces here that you guys see in this third picture, and they lasted throughout 2 entire competitions, getting slammed into. You can see the parts got pretty scuffed up and whatnot from us running into the walls and other robots running into us. But at one point, we did upgrade to a slightly different geometry that would allow us to, roll up to the wall a little bit more smoothly. In the first iteration, you see a robot actually hit us dead center, and they punched right in between where the 2 linkages are in the center right here, and they actually crushed a steel piston bore inside of one of our pneumatic actuators and bent the rod. But the 3D printed parts were fine, and they took the hit directly. So in the picture on the right, you can actually see we installed a crash bar behind that, and that just goes to show that these 3D printed parts that we ended up with in the end, they were actually superior in strength to some of the metal parts surrounding them, and that goes to show how far the technology really has come. So some quick design takeaways. So with SOLIDWORKS, we're able to quickly iterate in our process with very little cost. 3D printed parts simply cost less than machine parts. The flexible end component that replaced any need for machine parts really saved us a lot of time and money. Students are going to make mistakes, in our case, and it was really also a big time saver in that we didn't need to spend the time of machining, and time is money. So we would let this run overnight, and while that was running, the students were free to design other parts and do that. And then furthermore, the shape that we required, the construction type that required, you'll often find in manufacturing that you can model just about anything, but fabricating it is a completely different story. And 3D printed parts really take the cake in making stuff that you typically can't fabricate. So the next thing we'll talk about is simulation of failure. So for us, we often design parts that will go on our machine, and we won't know if they're going to be strong enough, and we just often enough have to kind of guess and check. So a couple of years ago, we built this robot. This is our 2018 machine, and down in the center of the robot, there was a winch that had to spool up a Dyneema wire that could pull about 1,500 pounds of force, and it would lift this large elevator up in the air. And we kept going back and forth on how to package this inside of the robot, and you can see that little red assembly is kind of squished in between a bunch of other things. And what it came down to was we were very unsure as to what orientation this assembly should be in. So we actually took it into SOLIDWORKS FEA so that we could take a look at it. So packaging this assembly was tough. You guys can see down here in red, we had to squeeze it in between our drive systems. We even had to hollow out some of the COTS item parts that we would typically see, and we had to move some stuff around to get this to work in the first place. So if we take a look at what that's going to look like in SOLIDWORKS, give that 1 second to show up on your screen. The first thing you do is simplify the geometry. Anytime you're going to do FEA simulation or finite element analysis to test for stress or deflection, you want to simplify the, you don't want to run through the whole assembly, the whole model. So we took just the supporting beam, the metal structures that we're going to test, these little gussets out of sheet metal, and then we simplified the motors, gearboxes, windings. We took all the gear teeth out of there. We took the windings out of the motor. Got some of that detail out of there, small enough to where you would want to mesh it and not cause any issues for your assembly. And the biggest question what we wanted to answer was, which orientation is best, straight up or 90 degrees. And then the second question we really wanted to ask was, can we rivet this in place, or do we want to use bolts? And simulation will let us do a fastener check and tell us what the stress in each hole is going to be. So at the first part of this, what we did was we bonded everything together. So with global contact set to bonded, we fixed the ends of the beam, and then we applied this external load, and we decided to put just a 50-pound load going up on this spool just to see what the reaction was going to be. So with those results, we could find the spool displaces about 0.010 of an inch, going kind of in that negative Y direction in the up. So if we run through a animation, and this is a drastically over-exaggerated animation just so you guys can see the behavior of the model. We've got a deformation scale of 208 up here at the top. You can run through a simple test and see how your assembly is really going to react. You can see that it's going to pull up, and we're going to see a little bit of twisting here. If this goes to a plastic deformation, you're going to see twisting in these brackets. Based on the stress of this bracket here in this corner is about 15 KSI. Strength of material for this aluminum is about 26. So we've got a pretty good factor of safety on this with it like that. But the question really was, is it stronger to put the load this way going to the right or up? So we ended up swapping to a little bit better of a study where we could put bolted contacts here in this, and we ran the exact same study. So we copied the bonded and we came to this bolted. So this will allow us to put some material science behind these pin connectors here and let us know if those are going to fail or not. So with this study, you would expect to get approximately the same displacement, not too much more, but because these brackets are now free to slide and rub against these pins, we did get more deformation, which makes sense. It's not as stiff of a structure as if everything was just, welded and bonded and glued together. But what the results will allow us to do is check our connector forces. And with our connector forces, sorry, let's go back into pin bolt checks what we wanted. We could go through and take a look at some of the stresses along these, and what we could find is the factor of safety at any one point in this with the connectors inside. If we're using steel as the fastener, we get about 1.4. So inside of the material, you can change each plug of material to see if you want to put an aluminum rivet, a steel rivet, or steel bolt, and then you can compare the stress at that location with the allowable stress of the bolt until if the bolt is going to fail or not. So we did it for rivets here, we did it for bolts, and we decided that bolts were the way to go, and we decided to use bolted connections for this overall. And then we came back and we copied that study from adding the bolt detail to this, and then we added the same study basically, but we changed the spool to 90 degrees. And what we found was that the displacement was a lot less, and the stress in the bracket was a lot less due to those loads. So we found that just by doing an FEA simulation, that this was the best orientation to actually design this for, and it passed both bolt checks and stress. Our factor of safety almost doubled simply by changing the direction of the load. So that told us right away that the best way to install this assembly would be in this configuration here, with the motors sitting straight up and the spool going straight up along the side of the beam. So we did this without building it, and that's really important for us. We have very little time to change configurations and whatnot during our 45-day build time. So being able to go in and do an FEA analysis will allow us to go in and make the correct decision quickly, and we can do a ton of comparative analysis. And the other thing that this told us was, even though we had a factor of safety of 4, if we look at what actually happened in the end, one practice robot had it at 90 degrees, and that iteration actually failed exactly in that spot where that stress told us it was going to. And it failed due to fatigue. It went through about 2 competitions, I think, before this piece shattered. But this piece did fail due to the fatigue load. The tower's going up and down, getting hit by other robots and whatnot. You guys can see the spool and the wire. This is in the up direction. So by putting it 90 degrees, we actually we kind of predicted exactly where it was going to fail, and then after a while, it finally did. So this gives us some confidence in our ability to use SOLIDWORKS simulation to check our designs for accurate failure. It's really easy to check for failure modes. You put in a load, and wherever it tells you that that high stress is going to be is typically where the design is going to fail. And then you can iterate digitally before you fabricate anything, and you'll know the factor of safety or the allowable load condition on the part before you get too deep in the design. So the last thing we're going to talk about is the Markforged technology and how we utilize that. So the part that we printed the claws out of were printed on the Markforged Mark II 3D printer. The Markforged technology is a dual nozzle FDM printer. And what it prints in for a base material, at least one nozzle, is almost always printing in onyx. You have the option to print in just nylon if you'd like, but nylon tends to fail due to temperature, and unless you need a very, very flexible part, most people opt to go with the onyx, which is a very durable polymer because it has a nylon mix, and inside of that nylon mix, there's microscopic pieces of carbon fiber that are chopped up and put inside. You have the option with the second nozzle to lay a line, a solid piece of just fiber, and there's multiple fibers that come with that. You can lay carbon fiber inside, you can lay Kevlar or fiberglass. There's even a high strength or temperature resistant fiberglass as another option, not pictured here. But you can lay these different fibers inside of the parts, and a carbon fiber fill or a Kevlar fill, these parts can be just as strong and stiff as aluminum, but a fraction of the weight. So this makes them extremely attractive materials to design with. In our cases, we really cared about dynamic loads. So I'll show you guys a part that we made. This part was a half split of the part that we created for the robot. That's half the claw you see there. So with that infill, with no fiber reinforcement, this was able to last us our entire season. You know, our robot could get up to a speed of about 20 feet per second and slam into a wall. You know, other robots pushed us around. They hit us on these claw pieces. You know, the assembly got abused in a multitude of ways that is, I would say, atypical of typical manufacturing. And these parts really stood up to the test of time, and they're still installed on the robots back there today, a year later. So these parts are lighter than aluminum. They're super easy to replace, and we were not going to cry if we had to replace these because of the cost. They're cheaper in metal than metal in a multitude of ways. The cost of the metal, as well as the fact that somebody has to machine the metal, so the time on the machine and the time to turn down the stock and whatnot, there's just no comparison on the price. They took dynamic impacts in a superior way. Metal parts are going to mar, they're going to mark up, they're going to mark up things, they're going to mark up the devices they're handling, like the discs. They're going to deform, and once they deform, they don't really spring back. These carbon fiber parts, when they're struck, they spring back. I actually took one of these and smashed it with a hammer, and there was a small indentation where you could see it, but it sprung back and basically retained its original shape. Aluminum, that divot would have been there forever. So there's a lot of advantages to using this technology. And for manufacturers, some of the top uses, I would say, are for jigs and fixturing especially. When you want to machine something like you see here, you want to install a toggle clamp, these machines are incredibly powerful because you can pause them during the printing, and you can insert things like nuts, inserts, strain gauges, etc. When you need to replace parts, you can have a strain gauge that reads off when the part is getting past its strain limit. You can retire it. You can do a lot of things that you can't do with traditional manufacturing that make this an attractive model. some of the things that we learned when doing this was that because of that weight savings that we get, and the fact that it doesn't mark up the payload, for manufacturers, end of arm tooling, like you see here on the screen, if you go to the Markforged site, there's a ton of end of arm tooling guides and fixturing guides. These replace the lathe jaws that you guys see in traditional manufacturing to hold parts because they don't mark up pieces. And you are also able to put some of these on the end of arm tooling for the actual robots themselves, and that increases the allowable payload that the machines can actually carry. So from a manufacturing standpoint, there's a multitude of uses and how to change some of your traditional machining methods and replace them 100% with 3D manufactured parts in just a few hours. For cost on these Eiger software that comes with the Markforged components really made this easy for us. We were able to take our part and put it inside of Eiger. We would get print time and material cost for just Onyx. If we wanted to change that, if we wanted to add reinforcement material, let's say we wanted to add carbon fiber back into this, we can go in and calculate, and Eiger will take the STL file that we've got, and it'll put it through the slicer like you see here on my screen, and it will allow you to sort of predict how you can put the fiber inside of the part and change how that fiber gets laid inside to change the strength of the part in different directions and whatnot. We actually ran through the entire season without using any fiber reinforcement on any of our parts. So once I added fiber to this part, it went up about $1 or $2, 9-hour print. And if we look at the internal view of the part on Eiger, we can actually see right now it's only putting fiber on this outside. So if we add fiber to about the middle here, you can sort of predictively add fiber in different places on these parts, and it will go through and it'll slice and put the carbon fiber here. You guys can see at the bottom how it's infilling. The Markforged printers also print their own support material that's really easy to tear off. It basically lays this little side-to-side, kind of like their logo, this Z shape or this S shape inside, this serpentine shape. And basically you can pull the part right off the printer, rip it out, and there's not a lot of sanding or post-processing required like a lot of other printers that you guys see on the market, and that you can just take this off and pretty much use it right out of the gate. The only thing I typically have to do when printing for hole patterns and whatnot is I usually push a rod or a pin through the inside of the part to push out material inside of the holes, or sometimes you can grab needle nose pliers, stick it down in the hole, grab that S shape and rip it right out, and it comes out like an accordion. So overall, these parts really these parts can be just as strong as aluminum you need them. Even if this part rolls out to a $200 part cost, it's still extremely cheap compared to what you would expend on an aluminum part. So going through about the full length of fiber on this one, you'd be looking at about $105 for this one. But if you put just slices of fiber, this one's quite overkill. If you put just slices of fiber in between some of these parts here, you end up, I think, maybe about $17, I think was what we looked at as some of our options. So this slicer makes it really easy to determine part cost. So what we really learned throughout this process, and whether or not 3D printed parts could replace traditional parts in manufacturing or not, is that everybody's right. Cheap plastic parts, they do fall apart and they do fail with traditional manufacturing methods. These are some PETG or PLA, cheap printed parts that we used on a, just a printer that's worth a couple $100. The Markforged is a desktop printer, so it's very affordable. It's very quiet. You can run it in an office, and they produce just amazing final quality parts. So for us, it was really a game changer in that we were able to upgrade from these cheap plastic parts that we cannot trust and we don't trust into some really, really robust, strong parts that we would be happy to use for a multitude of things. So in our experiences, the parts were actually better than aluminum. They were just as strong as aluminum. When we needed flexibility, we could model them without fiber inside. If we needed something to be really, really stiff, we would model it with fiber inside. They're much lighter than aluminum, and compared to the cost and time to retrieve aluminum parts of the same geometry, it was extremely cost effective for our team. So for us, it was definitely worth the investment to move forward with that design. So in closing, we took a look at some of the robotics case studies with the claw as our basis. SOLIDWORKS was able to let us go through and iterate on our designs very quickly, and we were able to take that directly to the 3D printer. Some printers actually let you export directly from SOLIDWORKS into the 3D printers, so SOLIDWORKS is there and prepared for that. Simulation of failure is something that SOLIDWORKS and that technology, the FEA technology, allowed us to do. So that was also a big game changer for us when we started teaching some of the students how to use FEA to do predictive failure analysis of our designs, and that's easy and simple to do for most cases, and only requires about a day or two of training to really get up to that standard. And really, any SOLIDWORKS user can use that FEA tool to do predictive failure analysis. And then lastly, we found that with the Markforged technology, we were really able to push our designs a lot farther. We were able to manufacture parts that we never really thought we could stick on the outside of the frame perimeter on our robot, because other robots would kindly remove that in the past. But overall, that technology allowed us to really be a lot more competitive and get our designs out a lot more quickly, and that really gave us a competitive edge for a game-winning robot. So I'll take any questions if anyone has regarding the SOLIDWORKS technology, FEA, or the Markforged topics we just talked about. I know it's right at the end of our time here. We are 1 minute shy of the end of the webinar, but I'll stick around for some questions. If anybody has that, you guys can enter those right into the chat. We'll take any questions you guys have. First question, I'll repeat the question for everybody to hear, is can you do FEA analysis of 3D printed parts? And the answer is yes, you can. So if you know what the material properties are, if you know the strengths in X, Y, and Z directions, you need to get modulus of elasticity, strength of material, and density, and you would also want to assume differently for different infills or different different thicknesses of the plastic on the outside. But yes, you can get strength of materials if you keep your print settings the same and model those appropriately in the FEA. So with FEA, the question is, what can you find with the FEA simulation, and what materials can you model? So with the one I pictured there, we were modeling all of those out of ductile materials. So that was like aluminum, steel, whatnot, stuff that has yield strength. That can be done in SOLIDWORKS Premium or Simulation Standard, and that will allow you to do pretty much anything with the yield strength. So any static stress analysis assembly will let you do any isotropic or orthotropic linear material properties. If you're doing some polymers and things like that, like you saw nylon and a couple of other things, you would need SOLIDWORKS Premium for that, but you can find stress, displacement, strain, factor of safety, and with Premium you can put in dynamic loads and things like that as well. Next question, do we have any heat issues with the Onyx? So since it's a nylon-based part, the Markforged technology originally had just nylon as the base. The nylon parts did have a couple of issues with heat if they're put into a heated environment, but with the Onyx, it has a much higher heat threshold because of the carbon fiber. And if you put carbon fiber or the temperature dependent fiberglass fiber on the inside of the part, it doesn't deform or degrade nearly as badly as just the Onyx or the nylon by itself. The Onyx already does a lot better in our experiences. There's even some NASCAR teams that are using these kind of close to like brake ducts and things like that, and they're actually seeing that they don't deform as much as they used to. If you're going to do a part like that in a heated environment, I do recommend running some fiber on the inside to increase the stiffness, and it shouldn't degrade as much due to temperature. Next question was, How often do you have to replace the cartridges? I would say it really depends on the volume of parts that you're printing. One spool of Onyx usually lasts us a couple of months, doing a multitude of prints of about that size and whatnot. Your mileage is going to vary depending on your production, but um, you'll get quite a if you're doing light infill, you'll get quite a lot of material out of a roll. Any other questions? All right. Well, thank you guys for attending. I do plan to take the recording of this webinar and put it up online if you guys want to share any of this. But thanks again for coming to our webinar today. We'll let you guys go right before lunchtime here, and hopefully we'll see you again next time. Thank you.